In this video, we will discuss new functions from old functions, which you've probably heard in previous classes as parent and child functions. Our learning objective is pretty straightforward. We want to be able to combine and alter functions. We can do that with algebraic equations, visual graphs, verbal words, and numbers. Some of the most common types you will look at are translations, vertical stretches or shrinks, horizontal stretches or shrinks, reflections, and also composition of functions. If you would like to pause the video to record this information, you may certainly do so. If you're in my class, this is listed on page 37 of your textbook. Same thing here. Right along the side of it, the short version is they go through and this information presents basically how do things get moved around. If you're doing a vertical or horizontal shift, it shows where and how the pieces would get applied. We already know horizontal is done inside the argument, inside the parentheses, and is the opposite of what you actually want. Right would be a subtraction. To shift to the right, you use a subtraction symbol, not addition. Vertical are done on the outside. If you're doing stretches and reflecting, same components. Stretches use multiplying and dividing. If it's a horizontal stretch or shrink, it is applied to the argument. If it's vertical, it's applied to the image outside the parentheses. Let's get started then. Given the base function, the parent function, y equals x squared, create a bunch of other graphs. Well, let's start here. Y equals x squared minus 3. You notice how it's a minus 3 not being applied inside the square? Well, that's what tells us it's a shift down 3, so we'll just say down 3, and I'm not going to go through and make really, really precise graphs and be really, really perfect with making sure they work out exactly the way they are, but we're getting a quick sketch. If we had the second one, x minus 3, you'll see that the minus 3 is inside the parentheses being applied to the argument. That tells us it's a horizontal shift, and those always go to the opposite. Instead of a minus 3, or instead of 3 to the left, that tells us it's 3 to the right. And we'd wind up with a quick sketch like that. I don't want this to get too crowded, so I'm going to erase these two pieces and continue working onward. Of course, you could pause the video, you could backtrack through the video if you wish to examine them further. Okay, y equals negative x squared. You'll note that this is negative x outside the parentheses. Because it's outside the parentheses, that tells us it's a reflection that's going down. So, reflecting it downward, we'd wind up with this graph. Please note the difference between that one and over here in the blue, where we have the negative inside the parentheses being applied to the argument. In that instance, this is a horizontal reflection left and right. But when we do that, reflecting it left and right, it's like, okay, we got the same thing. Remember, if you have y-axis symmetry like this, that happened because this is an even function. It fell on top of itself. That's fine. Secondly, or rather lastly, we have, I need a new color. Let's go with green. I haven't used that one yet. We have 2x squared. This is one where we will take each one of these and multiply by 2. This is a vertical stretch by a factor of 2. So 0, and then 2, and there, and we wind up with something that looks like this. Now, when we had done this in class, I remember people were asking, how can you tell the difference between a vertical stretch and a horizontal shrink? Because ultimately, When you create just this graph, they wind up looking really, really similar to one another. And probably the best way of doing that is to say not with visually. Visually, you can it's very difficult to tell the difference between a vertical stretch and a horizontal shrink. You actually do need to track through it with algebra. Specifically, in the original, we had the point 1, 1 and negative 1, 1. Where did those points get moved? If we were doing a vertical stretch like this one had done, when we plugged in x equals 1, that told us 2 times 1 squared was 2. So it got mapped and moved instead of being at, let me backtrack and phrase this a little bit differently. The original point, 1, 1, x equals 1, y equals 1. But after we applied the transformation, that point was no longer at 1, 1. It was moved to 1, 2. You'll notice the x coordinates are the same. It was the y coordinates that got changed. It was the y coordinate that got doubled times 2. The change in the y coordinate is what tells you it was a vertical stretch. If we were doing a horizontal shrink, that point would have been moved somewhere else. Instead of the point getting pulled upward to here, it would have been pushed inward to there. In that instance, when we paid attention to it, we would have had this point 1, 1 going somewhere to, for example, 1/2, 1. In that instance, the y values stay the same, and it was the x values that changed. That's how we could tell it was a horizontal shrink, because the x values got smaller. Visually, with the graph, it's exceedingly difficult to see that. But if you pay attention to where individual points get moved, it's easier to keep track of those kinds of changes. Ultimately, though, that little tangent did not have a direct correlate, did not directly show us how to do these particular problems, but it was an important observation that was based on a question that was asked. So, part 2, or example 2, sketch the graph of this function. Well, yes, you could type it into a calculator and get the answer quick. That's not the point behind this problem. The purpose behind this is to say you create your own sketch, not type into the calculator. If we had this parabola in the standard form, you probably remember it's easier to graph parabolas when we have them in this format, because then we know what the center is. We know where the vertex is at HK. But we don't have it. Well, we can get it, and that's the technique that we are going to use. In order to change this from the format here in the blue and get it into the format of the red, we will actually need to complete the square. Remember, completing the square is the process that said, if I have the right kind of number in the blank, then I can rewrite this into a format that looks like the red. The big part is, do you remember how to figure out the number in the blank? To get it, you had to look at this middle coefficient, the 8x. Please keep in mind, everything I'm saying is based on the fact that this is a 1x squared. If this was not a 1, we would not be able to do this process. We'd actually have to add another step before we're allowed to do this. But because it's a 1, we can start it off right away. We can take 8, cut it in half. What do you get? That's a 4. After you get the 4, square it. 4 times 4 is 16. That's the number that needs to go here. But of course, that's a problem because we've just took a plus 16, and where in the world did it come from? We've just changed it. When we look at the second equation, we now have x squared plus 8x plus 36. We didn't want plus 36. We need to have plus 20. We've changed it. Well, that's not too difficult to do either. We can go through and say plus something is going to give us a 20. So right now we have plus 16, add 4 more, and we have our plus 20. Well, there we go. The reason we were doing this was to take advantage of a theorem that we already knew, we already had. If we have something that is in this format, specifically in the format x squared plus bx plus b over 2 squared, we know that can be rewritten. We're taking advantage of a theorem you would have done in previous classes. It allows us to rewrite this as x plus 4 quantity squared. That's just the part in the green. But we still need to bring down the plus 4 that we had left over from the 20. Well, now that this fits the format in the red, we can go through and say, here's our vertex. We have negative 4, 4 for the vertex. Negative 4, 4, there we go. And we can start filling in the standard parabola shape now. And we're done. We have a quick sketch. Important characteristic, though, is making sure you get the vertex correct. In order to get the vertex, for this problem, we needed to complete the square. Our third example, sketch the following graphs. Well, if we're going to sketch the graph, we kind of have to keep in mind what do the parent functions look like, because if you don't remember what the parent function looks like, it's difficult to sketch the child. So, sketching the parent, cosine of 0 is 1, cosine of 90 is 0, cosine of pi is negative 1, and coming over and coming up. And so what we have is this shape. Here's our cosine function. This is the parent. So, for part A, what does this 2 do for us? Well, since the 2 is being applied outside the cosine, that's being applied to the image, that tells us we're going to make a vertical stretch. Everything is going to be made twice as tall. Important things worth noting then, a height of 1 is going to get shifted upward to a height of 2. A height of negative 1 will be stretched downward to a height of negative 2. But heights of 0, you take 2 times 0, you still get 0. So when we start filling in this information, all the peaks will go up to negative 2. All the valleys will go down to negative 2. But we need to keep the same locations where we cross the x-axis. So we'd have there, and here, and there, and here, and there, and then, and at pi, and there, and at 2 pi, we're up here. So let's start filling them in. There we go. This is 2 cosine x. And we're done. To make sure that we do not get this too crowded with part B, I'm going to erase the stuff in blue, just backtrack and progress from there. Oh, I did not want that. Sorry. Let me get rid of these blue dots now. Okay, so We will pick up with part B, and I'm going to start with this green. Let's track the transformations that are being done. First of all, what is the 2 inside the cosine doing? Well, since it is being applied inside the cosine, we know it's being applied to the argument. That is a horizontal shrink. That tells us all of the points are going to get brought inward half as far. Especially pi over 2 would get brought in halfward to pi over 4. Same thing with the negatives. 2 pi at the top would get brought inward to regular pi. Same thing with negative 2 pi. They get brought inward. Negative pi would have been brought inward to pi over 2. That pi would be brought into pi over 2, so we're looking at here. Just the transformation of having the 2, and let's see how well I can start getting this stuff filled in. And again, I'm doing a sketch, I'm not making it perfect. Okay. But it basically does this to it. The next piece we have is the negative sign. The negative sign is being applied outside the cosine. That tells us it is a reflection up and down. So this whole piece in the green needs to get flipped upside down. So we would have here, and there, and there, and right now I'm just kind of filling in the peaks, top and bottom, and saying fill them in. Okay, and it's looking crowded, so I'm going to take all the stuff in the green and get rid of the green. Get rid of the green. And all these little green dots, try to get rid of as well. There, and there, and there, and there, and there. Okay, I tried to clean it up. All right, now to finish this last part off, we now have the 1, which will take everything and shift it 1 unit up. So everything that was at this bottom baseline of negative 1 is now going to be shifted upward to sit on the x-axis. All of this stuff that was at a height of positive 1 is going to get shifted upward to the height of positive 2. Now, instead of redrawing it, I'm lucky that I have the smartboard because I can grab it and drag it up. Sweet for me. Nice little time saver on that part. And so we wind up with this general graph. Get rid of all the spare dots that I can without messing it up too much. And so that's what we wind up with. Obviously not a perfect sketch. If we wanted perfection, we'd excuse me. If we were going for perfect, we'd just take this and plug it into a graphic calculator and get a precise image there. But for a quick sketch, we should be able to figure out it's going to have this general shape. Example 4. The graph shows the number of hours of daylight as functions of the time of the year at several different latitudes. Given that Philadelphia is located at approximately 40 degrees north latitude, find a function that will model the length of the daylight in Philadelphia. Now, several things that we're going to point out. If we want to go for a perfect equation, it's going to take a little bit more work. We're looking for something that seems reasonable, is ballpark close, and so let's go from there. The important thing that we're looking at, though, of course, is Philadelphia is at 40 degrees north latitude, and this family of functions that they're showing are for a lot of different lines of latitude. We have 40, 30, 50, 60, and we are going at 40, which tells us this is the equation that we're going for. We must create the equation for 40 degrees north latitude. Take a look at the general shape of it. What shape is that? Well, especially if we were to continue and go further, following the pattern, that's a piece that you should recognize and say, wait a minute, that looks, especially with the especially with the translation, we bring this piece over, what kind of graph has that? This is one that we should recognize as a sine curve. Now, of course, we'd look at it and say, why not have it be a cosine? Because sine and cosine look pretty similar. Well, the big reason we're doing sine instead of cosine is where the peak starts. Remember, when we have x equals 0 for our angle, sine of 0 is 0, but cosine of 0 is 1. This is a graph that's already starting off at a 0, 0. If we wanted to, we would be able to say, oh, well, I can shift it over this way and have it start off at a 1 like that. True, we would be able to do that, but then we would be forced over here to be working with negative time, and maybe we don't want to work with negative time. I mean, do you really want to be talking about negative 2 months? It's just a little bit weird, it's a little bit goofy. We'd rather not do it, so we're going to stick with sine instead of doing cosine, although, yes, it would be possible to do this problem with cosine. It's just easier to do it with sine. All right, so since it fits the sine function, we have to start by figuring out some of the changes that got made. In particular, we can already see it's been shifted to the right and it's been shifted up. So we know we will have to do a translation up and to the right. But besides that, we also can tell that the sine function has an amplitude of 1. When you have this peak from top to bottom, the regular sine function has a height of 1, and this one doesn't. Since it does not have a height of 1, how many times taller is it? Well, this is at a piece saying it's 12. The peak here is tough to see, but I'm going to say, what, 15.6? Well, if that's 15.6 and 12, we can subtract those and get that this peak is about 3.6 times taller. So if we're manipulating our parent function, we had sine of x. Because it's 3.6 times taller, we can say 3.6. Okay? I'm going to erase the stuff in red now. But we also have, get rid of this. And I'm going to switch to a smaller eraser now so that I can try to, you know what? That's just silly of me. I'll just do this and delete it. It's smarter anyway. Okay. We also have the problem, though, that it's getting stretched out horizontally. Specifically, one whole cycle like this is supposed to take 2 pi radians. 2 pi radians is, we know, approximately 6.28. But when we are looking at our horizontal axis, where we're starting off May, June, all the way over to December, we are not getting 6 months. We are actually getting about 12 months. So specifically, 12 months, that's for the whole year, so that's 365 days. That's giving us a horizontal stretch then. When this stuff is getting factored out, the stretching factor that's doing a conversion, we're taking the 2 pi that it's supposed to be and instead stretching it out to 365. Well, if we want to get this stretched backward to what it's supposed to be, we will have to use that conversion rate and set it up as 2 pi to 365. That's what's happening with our time. So we would have this piece. Factoring in this piece with the blue, like we were considering with the 3.6, is actually indicating what's happening with this whole piece that's getting shifted. Additionally, we would need to look a little bit further and say, okay, well, we've stretched it vertically, we've stretched it horizontally, we still need to do the translation now. This translation, we will note, is up 12. To apply an up 12 transformation, well, since that's vertical, we know that's going to have to be applied to the outside. But we also have this piece where, excuse me, we also have it being placed a couple days over. Well, not a couple days. When we actually look at where this piece is, please notice that's being put over toward March. But what this is indicating for us is, excuse me, we have to get an estimate for about how many days this is getting shifted. At the beginning of the year, when we have time is 0, that's a piece that's January 1st. And when we get a time of 31, that's February 1st. The t equals part is actually keeping track of how many days have been completed. So at the start of January 1st, 0 days are done. At the start of February 1st, the entire month of January is done, and January has 31. And when we go to March, well, since February has 28 days, that would give us a total of 59. So when we back this part up and say, where are we getting pieced? We can see we've already started at March. We're not yet to April. If we continued this toward April 1st, March has another 31 days. So that would give us April 1st is corresponding to a time of 90 days. But we didn't yet get all the way to April. We're a little bit before it. How much would you say? 5 days, 10 days? If this whole piece is 31 days, how many days are we short? 5? Well, without more information, we're kind of guessing a little bit, but 5 days seems like it's pretty reasonable. Well, that tells us then, when we had our horizontal shift, we had the 12 vertical, but then the horizontal shift was an 85-day shift to the right. Well, that's going to tell us that we need to have the opposite for our 85 applied inside the argument. Now, because we're talking about x being time measured in days, I want to change it from an x to a d just so that I'm reminded what this piece is actually doing. And our entire formula then is the length of the day, the number of hours of daylight based on the number of days that have passed in the year. And so we get a formula that we can say, here's a guess. Here's our best case scenario. Is it perfect? No, because if we wanted it to be perfect, we would need more information. Like, instead of guessing that this is 85 days in, exactly how many days is it? Those are information that we would need to look at. And if we had a chart, we'd be able to get better information. But here we go with our graph. I really like this problem, by the way. To me, this is just really cool. You get your vertical stretches, you get your horizontal stretches, you get the translations. It's such a nice one that it's really fun for me. It's cool. Sorry to nerd out on you guys, but this is just really cool. Okay, example 5. Sketch the graph of the function absolute value of x the absolute value of x squared minus 3. This one's probably easier if we started by saying, just graph the stuff that's inside. What does x squared minus 3 look like? Okay, x squared, there, and 2 would get shifted down to here, and there, and then 9 shifted downward would be at 6. So I'm filling it in. Here's the graph of x squared minus 3. Since we're taking absolute value, please remember what absolute value does. If it's positive, keep it positive. So there we go. All the stuff that's above the x-axis is already positive. But if it's below the x-axis, make it positive. So if it's negative, you flip it and make it positive. Well, that's telling us the stuff that I have unhighlighted in the red needs to get flipped upward. Down 3 becomes up 3. Down 2 becomes up 2. And so we wind up with that shape. You could describe it as almost like a W shape, but you want to be careful saying it's a W because with a lot of excuse me, with a lot of W's, people will draw like a curve bottom. This does not have a curved bottom. It's a very sharp corner being applied at this point. Quick rehash. Tell me what these notations mean. Of course, f plus g of x is indicating you take two different functions and you add them up. F minus g, you subtract. Fg, you multiply them. F over g, you divide. And f with the little circle g, f composed with g, or f of g. This is the big one that is our function composition. You'll remember that's taking a function and plugging it into a function. So for example 6, let's do some function composition. F of g is saying we'll take g and plug it in for f. A lot of people like to do these mentally, and if you remember how to do these and you can do it mentally, that's perfectly fine. I'm going to show you a quick little trick that you can do. The outer part here is f. So just write down the function f. We're just copying what we had before. Now we'll make our way working inward, but we have g of x instead of the x. Well, every single place that you see the x that I have written in red, replace it with g of x. And not just writing g of x, but do this instead. So you can actually go through and just say, I'm going to, whoa, a little bit too much there. I'm going to erase the x. No, I didn't want to erase the whole thing. Come on, smartboard. Don't mess with me, man. Okay, so this doesn't like me, so since it won't let me erase, I'm going to outsmart it and say, screw you guys. I'll color you over in white. That x will instead get replaced with the other function. That's it. We're done. That's f of g. When we do g of f, it's the same thing. G of f of x, start off by writing down the function g. X minus 1 squared. But since our inner part is f of x, we can erase the other x and replace it with the other one that we had, 2x plus 1. And there we have it. Now this is one that simplifies pretty nicely. Plus 1 and minus 1 cancel, which give us 2x quantity squared. We know that we would need to square them both, so we'd wind up with 4x squared. And we're done. We can do the function composition. Number 7, do function compositions and find their domain. Finding the domain is going to be a little bit more tricky than the other part, but we'll do the same piece. Starting off with problem A. F of g says start by writing down the function f. That doesn't look right. I want to fix that. I don't like the way it looks. There's the function x. There is our function f of x. Erase every single x and replace it with the entire function for g. So this piece is erased and replaced with 4 minus x. There's our function. We have a root inside a root. To simplify this piece, it may be helpful to remember that a square root is a 1/2 exponent. So we have an exponent raised to another exponent. And do you remember the power to a power rule? If you have a power to a power, the rule was multiply the two exponents. 1/2 times 1/2 is 1/4, so we wind up with 4 minus x to the 1/4 power, which we could write with the radical notation 4th root. And so there we go. From here, we of course have to get the domain. We have the function. Check, we've got the function. Now we need the domain. Remember, the restrictions on the domain come from logarithms of non-positives. We have no logarithms. They also come from even-powered roots. You can't take a even-powered root of a negative number, square roots of negatives, so we've got that. We have to make sure this piece is greater than or equal to 0, or else we will have problems. And we also cannot divide by 0. But there's no division here, so we're good to go anyway. So when is this part true? Well, we can take plus x. 4 is greater than or equal to x. And just switching the order so that the variable's on the left, we'd have x is less than or equal to 4 is our domain. So the domain, everything from negative infinity up to 4. Should we include the 4? Yes, because 4 would give us square root of 0. That's okay, so this needs to be a square bracket, not the open parentheses. Okay, there's part A. I'm going to erase all this so we can start part B. Okay, part B, g of f. So g of f of x, we'll start by writing out g. And now everywhere there is an x, we will erase it and replace it with f. So There's our function. We wish that we would be able to take a shortcut and just say, oh, hooray, square root of 4 is 2, and then 2 minus the 4th root of x. Hooray, this would be such a wonderful shortcut, except remember, that shortcut's horribly wrong. You cannot split up roots that are adding and subtracting. You can only do that type of stuff if it's a multiplication or division of a root, not sums and differences. So there we go. We already have our function. It doesn't really simplify, but we need to figure out the domain. Now, 2 issues to keep in mind. First of all, we cannot take the square root of a negative. So with this piece here in the yellow, for just that part, we already have the restriction that x has to be greater than or equal to 0. Otherwise, we have a problem with the yellow square root. But we also have the bigger square root. Everything inside our entire radicand has to be positive, so we still have this stuff has to be greater than or equal to 0. So when we solve it, we could take plus the square root of x, and then we wind up with square root of x is less than or equal to 4. So what numbers will give us a square root that's less than or equal to 4? Squaring both sides, we'd get it has to be less than or equal to 16. Well, this gives us 2 criteria. We have to have numbers that are bigger than 0, or else we run into problems with the yellow root. But we also have to have numbers that are less than or equal to 16, otherwise we have problems with the blue root. When we put those 2 answers together, we have to have bigger than 0, smaller than 16, which we could write out in interval notation. Domain is everything from 0 to 16. You try plugging in a 17, and we're going to run into problems. We'll be forced to work with the complex numbers. We'll be forced to work with I, and we can't. Not in calculus. We work only with the real numbers. I'll erase this, and we'll start problem C. Okay, C is f composed with f. So f of f, starting on the outside. I want to use yellow. It's a prettier color. I feel like yellow today. I don't know why. But we'll take absolute value of x. Everywhere we see the x, we will have to erase it and replace it with another f. But we have the same problem here. This is half to a half, just like we were doing for problem A. That's x to the 1/4 power, or the 4th root of x. And very similarly to that one, that will have a domain of, oh, I needed a square bracket there, sorry. Everything from 0 on up is okay for an even-powered root. Erasing that and moving on to part D. We have G composed with G. So I'll start off and say G is the root of 4 minus x, but we'll replace that with another G. So when we erase the x and replace it with another function of G, we have 4 minus x. And here we go. This is very similar to part B now. This piece here in the red tells us this has to be greater than or equal to 0. And we looked at this exact inequality earlier. We already know that's a piece that tells us x has to be less than or equal to 4. but now we have the whole big root as well. Everything inside the big blue root has to be non-negative as well. So we have 4 minus x. That has to be greater than or equal to 0. So we have another inequality to solve. Adding it over, we'd have 4 is greater than or equal to this root. Squaring it would tell us 16 is greater than or equal to 4 subtract x. Subtracting 4 would tell us 12 is greater than or equal to negative x, or opposite of x. And dividing by a negative 1 tells us negative 12 is less than or equal to x. So we have x has to be greater than or equal to negative 12. So here we go. We have to have numbers that are greater than negative 12 for the large blue root to work. But they also have to be smaller than 4 for the red root to work. Putting those two together, the domain is everything from negative 12 up to positive 4. And we have our domain once again. Moving on to example 8. Find a triple composition, f of g of h, if f of x is equal to this rational function, x over x plus 4, g of x is x to the 5th, and h of x equals x plus 1. Please note the same strategy I said before. We have f of g of h. We can do this by starting on the outside. The function f, just write it down. X over x plus 4. Moving inward, we now have g. Everywhere that we have the x written, it needs to be erased and replaced with x to the 5th. So this x is erased, and we'll plug in x to the 5th. The other x is erased and replaced with x to the 5th. That will bring us inside now to h. Same piece. Everywhere you see the letter x, erase and replace. Erase the x, replace it with our function. Erase the x, and replace it with our function. Hooray, it's all nice, pretty colorful, trying to track through the whole piece, but when you actually write it out, bam. That's what we wind up with. Here's our function composition, just doing it in stages. Example 9 is working backward. Instead of already knowing the three functions f, g, and h, and then creating the composition, work backwards, where we have the composition already, you figure out the stages. My favorite technique for this one is to actually follow the order of operations. In order to create this f, we're going to start off with an x. What is the very first thing that's being done to it? Inside our parentheses, we have subtract 4. That gives us x minus 4. Then, what's being done? The next part is taking the sine of x, where we're taking the sine of the function, which gives us sine of x minus 4. What's the last thing that's being done? It's cubing. Because that gives us sine x minus 4 cubed. Please keep in mind the notations. I have this part written down here where we have the whole big sine as a cube. an alternate way, an alternate notation for that, just because it's shorter and easier for computers to handle and type. Okay, want to put that back up, is to erase this. Actually, let me put all this stuff back on. Oh. Okay. Okay. I lost my spot. Okay, there we are. This notation here on the right. Sorry, I got lost in my spot. This piece right here can instead be written this way. You need to remember the notation. Anyhow, the whole point for why we're doing this is these three stages, the subtract 4, take a sign, and take a cube, those are the functions that we can put together. The first thing we did was subtract 4. The second thing we did was to take a sign. Third thing we did was to cube. You'll note all I'm doing are taking these steps and I'm writing them out as functions using the x. Now, why did I do them as g, as h first, then g, then f? Because when you're evaluating, there. When you have nested functions like this, when you have a nested composition, it's like you have to break your way out. If you're inside the egg, you have to crack your way going to the outside. So H is the first piece to escape, then G, then F. So it's first, second, third. And that finishes us off. Go back to the learning objectives. Keep in mind what we were discussing. From this lesson, we were looking at reviewing skills on how you could combine or alter functions. We know that you could do that visually with the graphs. How do you move graphs around? We did a lot of those. We did not do any examples where we had to do adding and subtracting, multiplying, dividing functions because it's been my experience, students generally remember those, so we did not take time to go over and do these. And in part, we didn't do that in the video because when we had it in class, people were able to instantly tell me what they needed to do, so we don't need those examples for add, subtract, multiply, divide. But function composition, remember the structure. It's a way of combining functions and keeping track of domains so that we can just list out what's going on so that we can combine functions and still keep in mind what makes sense. All of those pieces are based on the parent and child functions. How can you create new functions from old functions? And our primary techniques that we were focusing on today, algebraically with a ton of equations, visually for the graphs.